Hey everyone, in this video we are going to learn about Rust, and it's going to be a tutorial aimed for intermediate programmers, as it's going to be a bit fast-paced. Why Rust and what is Rust? Rust is a fast and safe high-level programming language without a garbage collector. And why use it? Performance, you can go as low level as C. It has a rich ecosystem, which means that you get many libraries for the problem that you are trying to solve. And best of all, it has the best tooling in all the programming languages that I have ever encountered. So let's dive into it. To install Rust, you can go to rustlang.org and just copy this and paste it into your terminal. I already have it installed, so it's gonna be faster for me. But after this, you should have Cargo installed in your system. And we can just create a new Cargo project by doing Cargo new, and let's see, hello world. And after this, we should have the Cargo project. We can just cd into it and run cargo run, and we can see hello world. Let's see the project. We can see it that we just have a main function that prints hello world. First, let's review the basic data types. For Boolean values, it's gonna be bool, and the values are true or false. Let's create a variable called a. Let is how you create variables. And let's see, let a equals true. It's gonna be a type Boolean, as you can see here, and every line should be terminated with a semicolon. There is an exception that I will cover later. Then characters, they can be defined with a single quote, for example, A or V, and they are supposed to be UTF-8. Let's see, A. This is a character. We have the unsigned types, integers. We can do C, and let's type 42, and by default it's gonna be an assigned integer I32, but you can override this by doing U, and you have here all of the unsigned integers: U8, 32, 16, 64, and 128. Let's do U32. Then the signed integers, that can be negative, same, -2, and let's see, I, and it's the same as U, I8, 16, 32, 64, 128. Then the floats, it's F16, 32, 64, or 128. By default, it's gonna be the F64. And you can do, for example, 64 and .0, and that's how it's gonna be defined. Then strings, it's technically not a string, it's a string slice, but we'll cover the string later. They are defined by doing like this. You can say hello world, and the same. Then variables can be shadowed to take on other values. For example, we can say let f equals 69. And what's happening here is that technically there are two variables, but this second variable is taking the name of f, and this variable will be shadowed, so it will be no longer available after you declare this variable. Variables are immutable by default, so if you want to reassign them or mutate them, you must add a mute token after the let keyword. That way you can do f plus equals 1. That way you are incrementing. Or you can even do f equals 70 and you are reassigning the f variable. And comments are with a double slash. This is a comment. And if you want to define another function, you can do so by doing fn. And let's name this function hello. You do a parentheses. Here goes the name of the arguments if the function takes any. And then a return value if the function returns a value. If it does not, this is the return value. That's a tuple or void. You can think of it that way, but you can omit this. And for example, let's say this function returns a U32, and you can say return 42. This is the normal way. Or in Rust, you don't have to specify a return. You can just do 42. And in this case, you don't need a semicolon. It will just be a syntactic sugar for a return 42. And let's print all of these values. Here's how you print a value. And A, B, C, D, F. Okay. So let's run this program and cargo run. And as you can see, A, true, B, A, which is a character, C, 42, D minus 2, E 64, and F, it's not going to be hello world because we shadowed it with 69 and then reassigned it to 70. So this is going to be 70. Let's cover now control flow and loops. Let's just comment this out and say we don't need parentheses for the if condition. So we can just say if f is less than 100, which we know it is, then print f is less than 100. Else we can just print that f is greater than 100. If we run this, we can see f is less than 100. That's the if control flow. Then we have a loop. This will keep just looping forever. And since we know that f is mutable, we can just loop this over and say f plus 1. And if f is greater than 100, break out of this loop and print f. And let's see what happens if we run it. As we expect, it's 101. This can be turned into a while f is less than or equal to 100, and run this. It's gonna be the same output. We also have the for loop. Let's create a string slice or an array. You can think of it that way. Let array of characters is equal to, it's just the square brackets, and we set a single quote A, B, and C. This is gonna be char array of 3 elements, and we can do for character or whatever you want to call it in R, and we can just print the character. And if we go and run it, we can see in the output A, B, and C. Ownership is the mechanism that allows for memory safety programs. This does not come without a cost, so we are gonna review the rules. So far, we have only used simple data types that live in the stack and are cheap to copy. They implement a trait called copy. Think of it as an interface. And whenever you pass them around to another function, they are just copied. But for data types that live in the heap, for example, a string is one of them, the ownership rules apply. Let's review them. Let's declare a variable called a, which is a string. You can declare a string by using this syntax: string from, and you can pass in a normal string slice. So let's say hello world. And in this case, the variable a has a string hello world that lives in this scope in the function main. Once main ends, this will be deallocated and cleaned up. So let's say we have another function called foo, and we want to pass around a reference of this hello world. We can just do reference to a, and if we declare the function foo, we can say the argument will be of type str and will not return anything. So we can do print line, and let's print this. So after this line, since we only pass this as a reference, we can still use the variable a. It's still alive and well. But if we pass by value, let's say a, and turn this into a regular string, this works and compiles perfectly fine. But if we try to print a in this line 8, we will have a compile time error that says that the value borrowed here after move, because this value was moved into function foo, and that was the end of the lifetime. Let's go back to how we had it, where we passed this by reference. Also in Rust, we have a rule that we can only have one mutable reference at any given moment, or any number of immutable reference at any time. So let's dive into this. Let's assume we wanted to create another variable called v that is a mutable reference to a. To do that, we have to declare this as mutable. And now here in v, we can do manipulations of the string. For example, we can push another exclamation mark. If we try to do this after this line, we are gonna get a compile time error, because, like I said, you can have only one mutable reference at a time. So we still have a mutable reference in line 11. And at the same time, we are passing a reference to foo of a. So we cannot do that here. As we say, immutable borrow occurs here. This is one thing to watch out for. There's another concept called the string slices. Let's say we declare v again, and we want it to be a slice that points to hello world. So we can just do, we have a reference to a, and then we declare square brackets and just do ... and that means we are pointing to all of the slice in a. Or we can even declare, for example, if we wanted only the first character, we can say 0 to 1, and in this slice we will only have the value h, or if we do 2, we will have, and let's print this so that you can see this. And if we print it as we expect, we have he. And there are also array slices, we can do the same thing. For example, let's say we have 1, 2, 3, 4, 5, and we want to take a slice of this. We can just do it the same way. Just C, and then dot dot, and we will point to a slice of 1 through 5. Let's print it out. So for this case, we need to use this syntax because we need to do a print debug instead of a normal print, but it's the same, just take it as syntax. And yeah, we get 1, 2, 3, 4, 5. Structs and enums are the product and the sum types of Rust. We are also going to review tuples. Tuples are like structs, except they don't have named fields. And we're also going to see how we can pattern match against structs and enums. To define a struct, you can do so by doing the following. Struct and the name of the struct, let's say person. Structs don't necessarily have to have a field. They can just be blank structs, like in this case, struct. For this line, don't get scared. This derived debug is just a macro so that we can print the person. And let's try to print this person. So if we print it, we get person. And let's add a field into this person. Let's say age, and it's going to be U8. And for now, we need to define an age. Let's do 25. And we can print out the person. Or if we wanted to print out the age, we can do the age of the person is person.age. And that's how you do it. Now, for enums, it's a similar syntax, except you do enum here, followed by the name of the enum. In this case, let's do a color and all of the variants of the enum. So black or white. And let's try to define a variable for a color. Let's say color variable. And it's gonna be color double colon black. If we try to, the color is color variable and we run it, we get the color is black. Now for tuples, tuples are like structs without a named field. So we can say let person, and we can do it in a parentheses. That's how you define a tuple. And if we do 25, that represents it's the tuple that has only one element, 25. So we can access the element by doing let is equal to tuple person.0. If there is only one element, you need to put a comma afterwards. And we can print the age. The age is 25. And lastly, we can match against structs and enums. For example, if we wanted to match for line 15, we can match person. And in here, we can put patterns that might possibly be there. For example, for the age, match person.age, it can be any U8. So if the age is 25, if not, this is how you do it, then the age is not 25. You can also do like any other value, like 0, the age is, etc. For enums, it is the same thing. So let's say match color variable. And the only two possible values are going to be color black and color white. So if it's going to be color black, we can just print it to the console. And if we run it, we get the color is black, just like we expected, because color variable is color black. Also, for matching on structs, you don't have to match necessarily on a field. You can match like this: person age, and this will match a person, any person that has an age. But if we want a constraint, we can do this syntax: if age is greater than 20, and then we can print the age is greater than 20, or else the age is less than 20. That's how you match against an enum and a struct. In Rust, there are two very important types that signal errors as values, and these types are the option type that has two variants, and it's gonna be either a sum of a type or a non-value. And there is a result type that can have either an OK of a type, can be whatever type, or an error of another type. And these are used for error handling. Let's see how we can instantiate them. So in option type, we can just create a variable. And for an option type, we can do either it's sum of u32, and this is going to be of type option u32. You might ask how to extract the number, the u32, out of this option type. We can do b is a u32, and we can extract the type by just doing a.onWrap, and that's how we get the type. If we have another variable that's the same type, an option of a u32, but in this case, instead of some variant, it's a none, which is definitely possible. And we try to unwrap it like we did in this line number 6 to extract the u32. We can do this, only that this is going to result in a panic. What is a panic? Let's try it out and see what happens. So if we run this program, we're gonna see that thread main panicked at line number 8 on column number 20 by doing an unwrap. This is basically the program is just quitting and exiting. For result types, it is the same. We're gonna shadow the variables we defined earlier. So let a is it's of type result of, and the OK variant is, let's say it's the same u32, but now we need to have also an error type. For now, let's define the error just as an empty tuple. And let's see, a is an OK of 42. And as you can expect, we can do the same thing here. Let b equals a dot onWrap. And it's the same behavior as you saw above. Now for matching expressions, in the previous section, we saw the match expression. We're gonna review it again, so we can do match A, and we're gonna match some possible variants. So for example, let's do OK of any value, and this is gonna match any value that's an OK. Or if it is an error, then the error will be assigned to this variable, and we can do any logic. This is the match expression. Then we can do an if let. So we can say if let and OK, and let's see, 42, it's equal to A, and this is a pattern that you can, and if it matches with this variable, then this block is going to be executed. Not only you can do an if let, you can also do a while let. So you can say while, and here goes the pattern. While let OK x is equal to A, and let's print this line. This is a loop. Okay, if we run this program, you can see that this is just going to loop over and over in here, because it is always going to match an OK of a value. Another very important feature of Rust in error handling is the question mark operator. What the question mark operator means is that if you are dealing with a result type and it is an OK variant, by doing the question mark after it, it will extract the value out of the OK. But if it's an error, it will propagate upwards to the next function that called it. So let's do an example. Let's say we are dealing with A that has an OK of 42. To implement the question mark, then parent function should have also the same signature. So we need to make main to also return a result type. And here we can return whatever type we want as a value, but the error needs to match the same type of the errors that we are using with the question mark. In this case, the error is a tuple, so we can just do it also with a tuple. And here we can say let C is equal to A and the question mark. And we just extracted the value out of A, but we need to return from main a result type. So we can just say OK and a unit type. And now if we print C, C is C, and we go to the console and run it, we can see C is 42, and this is the U32. For this section, we're going to review collections and iterators. Let's start with vectors, which are dynamic arrays in Rust. So let's create a vector of string slices. Let's do let a is equal to, this is how you create a vector using the vec macro. And you can do hello and world. This is a vector of two elements that are strings. Then we have hash maps. Hash maps are key value stores like objects in JavaScript, and you can create a hash map by doing hash map :new, and you must define the type of the hash map. So let's do a hash map of U32s to a string. To insert items into a vector, you have to add a mute as well as in a hash map. And you can insert items by doing a.push, and let's add an exclamation mark. Let's print a, and we should have hello world and the two exclamation marks. Then for hash map, you can insert items by doing b.insert, and you can add a key. So let's add the key 0 and the value of hello. And let's run, let's debug and print the hash map. So let's see. Print. And if we print it, we get a 0 that is hello. And you can remove items by just doing b.remove and specifying the key. For vectors, you can remove items by doing the same, remove, and you will have to specify the index of the element, and it will shift all elements after it to the left. There is a very powerful concept in Rust that is called an iterator. Basically, an iterator is just a way to traverse a collection of items. And once you create an iterator, you can also perform manipulations to that iterator and create new collections. Let's do an example. So let's say we wanted to make a an iterator, and we can just define a new variable. Let v is to a dot iter, and that's how you create an iterator. And this is very useful if, for example, you want to loop over all of the items. So you can do for item in b, which is a iterator, and you will consume the iterator, and you can now just print every item. Let's print this so you can see hello world and exclamation mark. Note that you can just inline this variable and it will have the same effect if we run it. So iterators also have a method that is called next that can retrieve the next item, and it's either going to be none if there are no more items left, or a sum of the item. Let's go back to how we had it separate. Instead of iterating through all of the elements, we can do let first element, it's equal to b dot next, and this will give us an option of a string. We have to make this mutable though, because we are mutating the iterator. And here we get an option of a string. In this case, we know that there is a first element that's hello. So let's print this. And we should get, let's run this and we should get hello. Or we can even do first dot unwrap to unwrap the value, and we would get hello. You might ask, what happens if there are no elements? So let's just remove every element and let's specify a type. And what happens if we print line first and we run this? We are gonna get a none because there is no next value in this iterator. To convert back an iterator to a vector, you can do let c is equal to b dot collect, and you can collect this again into a vector. We do this underscore because it can infer that we are trying to collect string slices. Let's say you wanted to manipulate the data in an iterator, for example, do some form of map or filter. You can do this with the iterator by just doing on an iterator, for example, B, just doing a map. Or you can even do a filter. These methods accept a closure. You can think of closures as anonymous functions that you can access variables from the environment. For example, in this case, you could access A or V. And for example, let's say we wanted to make a transformation in C. We can just do a vector of U8, and we're just going to return the length of the element. And here we can do collect. This returns a U size. So let's change this into a U size. And if we print C, we now have a new vector of the length of the initial elements. And let's print this out so that you can see it in the console. If we do cargo run, we can see 5, 5, because the length of every word is 5. We can also do filter here. And let's say if element dot length is less than 5, then we want to return true, meaning that we want to keep it. Else we want to return false, meaning that we want to filter it. In this case, this is going to be a vector of string. And if we print this out to the console, we can see that there are no elements because we are filtering out if the length is less than 5 and they are 5 or greater. I'm going to try to make the examples as simple as possible, even though they might be a little contrived, but let's jump to it. Suppose that we want to define our own struct that is just a wrapper of a vector. So let's call it my wrapper. And inside of this struct, we want to have a vector, but we don't know yet what the vector might have. So we can just define a generic. To define a generic, we can just set a t or whatever name we want to call it. And the syntax is after the name of the struct, we can do the angle brackets and put in the same name, t. We can name these whatever, a, but we're gonna name this t for now. So this way we could just create instances of this struct by doing my wrapper and then a new vector. And let's say in this case we want a vector of booleans. We have a my wrapper of bool, and we can now create another variable that has a vector, for example, of u8s, and we can just type this, so we make this explicit, u8. This is the advantages of working with generics. The same syntax applies in functions. Let's define a function that calculates the length of the elements in the vector of my wrapper. So we can just create a function, calculate length, and we are expecting my wrapper of t, but we actually have to specify here that we are gonna work with a generic. So this way we can just return a usize that is an unsigned integer of a.0.length, and that is how we specify generics in functions. We could, of course, convert this to an explicit return, and it is exactly the same thing, but in Rust, for the last line of a function, if you omit the return and omit the semicolon, it will be the return value. Now let's go to traits. So in Rust, in the standard library, we have this trait called a default trait. Think of traits as an interface, as I mentioned already, but this default trait, in order to implement it, you must implement a default function that returns a self. In the case of our wrapper, my wrapper of t, self would be my wrapper of t. So let's implement the default trait for my wrapper. The syntax to do this is impl, and we can just autocomplete this. Impl t default for my wrapper, and we need to specify the function default that returns a self. So if we wanted to just return the struct with an empty vector, which is the default behavior, we can do my wrapper and return an empty vector. That way we already have a default implementation. So we could do in our program, let's see, is equal to my wrapper, double colon, and default. And we would have already a default value, but we need to type because Rust can't infer it by this usage. So we can do my wrapper, and if we wanted to use booleans, we can just do bool. These are the simplest examples I could think of generics and traits. And the only new syntax that we introduced here is the self and the impl. Self is syntactic sugar. We could here just do, instead of self, my wrapper of T. And an impl just means that you are implementing functions for that specific type. And that's it. I'm going to use an example that everyone uses, but I like it. So let's say we have a function that calculates the length of two string slices and returns a reference to that string on the largest one. So let's implement it. Largest string. So the logic is very simple. If the length of A is greater than the length of B, then we will return A. If not, B. And this is the syntax: angle brackets, single quote, and the A. This can be any name, but normally it's A, B, C, etc. And let's create some examples. Let one is equal to hello to string. Okay. We have two strings and we are passing the two string slices to the largest function. As you can expect, if we run this, we're gonna get hello with two exclamation marks because that is the largest string. And you might ask, why do we need a lifetime? So imagine that we dropped any of these two variables in this block, and here it will get dropped. So for example, let's say let some variable is equal to 2. And if we didn't get a compile error and we printed out this result, we would have a dangling reference because this string hello does not exist anymore. So if we go to the terminal and try to build the project, it will complain and say that the borrow of 2 occurs here and we moved in this block and we are later trying to borrow again. So that is undefined behavior and this is not possible in Rust. So that is why you need to specify the lifetime annotations in the cases that Rust cannot infer the lifetimes itself, like in this case. And we are forcing these two lifetimes to have the same lifetime. So it doesn't matter if we do this on this variable 1, even if we're not using it later, because we are explicitly telling the compiler that this return reference is of lifetime A. And since that's result, it's gonna link this with here. And that's why it's gonna complain. For structs, let's say we have a field A that is a reference to a string slice. Rust immediately is going to tell us that it expects a named lifetime parameter. And it even gives us the syntax to do, so we can just copy and paste this. And that's how you define structs with a lifetime parameter. And to use it, you can do, let's do an underscore because we don't really care about the name of the variable. So we can say my struct, and for the A, it's going to be hello. Let's say we wanted to create another module for main, so we don't define everything in here. We can just declare the module. For example, let's say we want to create an adder module. we can just create a file under source called adder.rs, and the module is already created. And in here, we can create public functions so that main can import them. For example, pub, which makes it public. And let's say add, that takes then two I32s and returns an I32. We can just under main just use adder :add, and that's how we can use the function add. Let's see, 1 and 2. And the underscore just means discard the value. If we wanted to import everything in the module adder, we can just do asterisk, and we import every public element in there. Let's create a struct. We have it in our namespace A, as you can see. Suppose that we had a public struct here in main that's called B, and we want to import here in the module adder. We can do so by doing use and super B. What super means, it's just referring to the crate, and it's like the parent module. Also, in Rust, you have all of your dependencies in cargo.toml. To add a dependency, you can either add it manually, or you can just in the CLI do cargo add and add a dependency. In this case, let's add one that's called anyhow. And as you can see, it added the dependency here in the cargo.toml. Also, crates, think of crates in Rust as just generally packages that you can import. Now let's talk about tests. Let's say we wanted to test our function add in the module adder. We can do so by doing this syntax, just cfg test, add a module test, and under here we can create tests. For example, function it works, and we can just import the function add, or we can even just do super, and we can just run the tests by doing cargo tests, and yeah, it works. Also, I forgot to mention that you can define modules not only by declaring them parent file and creating a new file for the module. You can also do it. Let's delete this file, and you can also do it this way. Declare it right here and just do pub function add. And this acts like an isolated module for main. Yeah. For this lesson, we're gonna review advanced error handling and a very cool crate that everyone uses that's called anyhow. So let's get into it. Let's say we wanted to read the contents of a file. There is a function in the started library called the read to string that takes in the path to file. This function returns a result, and for the error variant, it returns an error that comes from the standard IO module. So this is cool if we, let's say we wanted to use the question mark in here. To do that, we would need to return a result that is compatible with the error for this. So we would need to return a standard IO error. And this way we could do the question mark in here and just return an OK from here. This is cool and all, but suppose that we had our own error, our errors, and we had this different variant, and we had a function called, I don't know, foo, that returns a result of a unit, and for the error variant, it would return our errors. Let's just return an error of our errors A. What if we wanted to use foo in here and do the question mark? It would immediately complain because those two errors are not compatible and they can't work together. So to solve this, we could either change this error to be of type standard IO error so that they can be compatible, or transform this error from read to string into our own custom error so that we can use both. But that would be a lot of boilerplate or some hassle to do. And instead, we can just rely on this library that's very popular called Anyhow. Let's install it. This library provides its own result type that you don't have to specify the error variant. You can just omit this and specify the OK value. And for this IO error, it will transform it into its own anyhow error. And what we could do here for our own errors, enum, it's just implement this trait called from our errors, and we can transform it to an anyhow error. What this anyhow macro does, it's that it creates an error from anyhow. So let's just import this instead. This is the macro. It also exposes much more stuff. Now, if we just do foo and the question mark, it works. And if we don't even want to have our own custom error because it doesn't make sense, we can just instead return from foo directly an anyhow error. So if we do let error and just do the macro that I showed and do this is an error, you can see the type of this variable. It's an error, and it will be, if we want to type it, we can do anyhow error. And we can just return this error and everything works perfectly because all of the errors match to be of the same type. And also this is just an alias for anyhow error, by the way. We can omit this generic because what this library is doing is it will be transforming all of the errors into an anyhow error to be unified, and it makes life so much easier. So let's just omit this. Also, there is a shorthand for this pattern, error anyhow. We can do veil. That's another macro. And just do this is an error. And it will do exactly the same thing. It's just less boilerplate. Also, suppose that we wanted to manipulate the error that this function gives. For example, if we run this, it will say error, no such file or directory. But what if we wanted to add more context into the error? So we can import this trait called context from anyhow. And in here, we can just do dot context and add our own custom string. Like, for example, I don't know, this is context. And if we run this again, we will see error. What we added, this is context caused by no such file or directory. So this is very useful as well. For this last lesson, we're gonna review a library called Tokyo that everyone uses, and it's very important to understand how to use it for concurrency and asynchronous programming, so that you can use the async await that we are all familiar with. This library works on a high level by introducing a runtime with tasks that can run your code. Don't get too much into this because it is very complicated, but it is very easy to use and you don't need to know exactly how it works to use it. So just to install this runtime, you can do cargo add Tokyo and provide the features full. What this gives you is a macro called Tokyo main that you can just put in function main. And this way you can make function main asynchronous by providing the async keyword. And this library Tokyo exposes a lot of modules and functions that you can use that even replace some of the standard library. For example, for file system, we reviewed in a previous video the read to string. This one also provides its own read to string, but the difference is that it's an asynchronous version of read to string. So if we do let contents is equal read to string and provide a path, it's the same thing, only that for this case, to actually execute the future or the promise, as you can think of it in other languages, you can do at the end dot await to run it. And if we run this program and try to print out the contents of the file, we are gonna get the same result, no such file or directory. This is the same behavior that we had earlier. The only difference is that we could have, for example, another function here that does the same, and we can introduce concurrency into our program by doing, for example, let's say a try join. And if we do this, these two calls will be run concurrently, so neither will block the main thread. And this is a huge benefit for your programs. Generally, you don't have to work with a join. If you're starting out, you can just do how we did it previously with a await in and do sequential operations. That's going to be the same generally as doing it without Tokyo, but for many libraries that you are going to use, for example, request, they work with futures unless you use the blocking version. So you generally just have to rely on this runtime Tokyo. And yeah, you can just dig further. It's very interesting and it has a lot of stuff. But yeah, peace.